Hi, Zundamon. I'm studying pinch-off in MOSFET now, but I'm having trouble understanding it.
What don't you understand?
I have 3 questions. First, why does the channel be pinched off in the first place? Second, even if the channel is pinched off, why does current still flow? And third, why does the drain current saturate in saturation region? I'd like you to explain these without using too many equations, just in a clear way.
Okay, leave it to me. In this video, I'll explain these questions following this outline. Let's get started. Before answering the question, let us briefly review what pinch-off is, using this typical N-channel MOSFET. In a MOSFET, when a large voltage is applied to the gate, a conductive channel called the inversion region forms at the semiconductor surface under the oxide. At this point, applying a voltage to the drain, electrons flow from the source to the drain through the channel. This flow is called drain current. Initially, as the drain voltage increases, the drain current also increases. This is called linear region. However, this increase gradually slows down, and the thickness of the inversion region near the drain also gradually decreases. After that, when the drain voltage reaches a certain value, the thickness there eventually becomes 0. This is pinch-off. After pinch-off occurs, the current does not increase even if the drain voltage is further increased. This is called saturation region. In other words, the occurrence of pinch-off can also be considered the onset of the saturation region. This concludes a brief review of pinch-off. So, let's start answering the questions in the next chapter. Now, let us consider the first question. Why does the channel be pinched off? The answer is that the potential near the drain increases, causing the inversion region there to disappear. This becomes clear when considering the equivalent circuit of a MOSFET. The equivalent circuit of the surface can be designed like this. Some of you may be seeing this circuit for the first time. There are only 2 points to keep in mind here. One is that the oxide layer serves as a capacitor. The other is that the capacitor near the source is affected by the source voltage, while the capacitor near the drain is affected by the drain voltage. Well, strictly speaking, it's more complex. But let's set aside the details for now and move forward. Now, let's apply a gate voltage larger than the threshold voltage. This causes a large number of electrons to accumulate at the semiconductor surface under the oxide, forming an inversion region that serves as a carrier path. Here, the inversion layer behaves as an N-type semiconductor. Incidentally, the reason why an N-type inversion layer appears locally in a P-type semiconductor is that potential below the oxide increases. This is easier to understand by looking at the band diagram. In inversion region, the intrinsic Fermi level is below the Fermi level by applying Vg. It is well known that whether a semiconductor behaves as N-type or P-type is determined not by the doped material itself, but by the relative positions of Ei and Df. This is crucial for understanding why the channel becomes pinched off. Next, the drain voltage is gradually increased. At this point, drain current begins to flow. But simultaneously, the inversion layer near the drain gradually narrows. This is because the potential in that region increases due to the drain voltage. Let's look at the band diagram at this time. Note that Vd shifts the Fermi level downward, reducing the region where Ei is less than Ef. However, the inversion layer does not disappear completely yet. This is because the region where Ei is less than Ef still exists. Then, as the drain voltage continues to increase, when it reaches a certain value, the inversion region of the drain completely disappears. This is the moment the channel is pinched off. This is because Ei is greater than or equal to Ef in all regions near the drain. Incidentally, the point where Ei is equal to Ef is the pinch-off point, and the drain voltage at which pinch-off occurs is generally denoted as Vd-sat. Then, if the drain voltage is further increased, the region where Ei larger than Ef extends toward the source. This means that the region where the inversion layer disappears expands toward the source. And this is precisely why the channel is pinched off in the saturation region. This is the answer to the first question.
Thanks, Zundamon. I understand. However, I have one question. If the channel is pinched off, doesn't that mean no drain current flows?
That's a major misunderstanding. Drain current does flow. Let's explain the reason in the next chapter. Now, let us consider the second question. Why does drain current flow after pinch-off? The answer is that carriers are attracted by the strong electric field in the depletion region between the channel and drain. This electric field is formed by donor ions and acceptor ions. It's easier to understand if we use a p-n junction as an example. Generally, a depletion region is formed when p-type and n-type semiconductors contact each other. And electric field is also formed by donor and acceptor ions. It's the same in MOSFET. A depletion region is formed between p-silicon and n+, and a strong electric field exists there. Carriers that have passed the pinch-off point are strongly attracted by this field, so drain current flows even though the channel is pinched off. This may be easier to understand if we consider it in a band diagram. The figure on the right shows the band diagram between A and A' in a MOSFET. Since many people are likely seeing this diagram for the first time, let's take a look at it step by step. First, when VG and VD are 0, the potential looks like this diagram. Notice that carriers cannot move from the source to the drain due to the potential barrier. Next, VG is applied to the gate to form an inversion region. Notice that the barrier is lowered, allowing carriers to move between the source and drain. Then, when VD is applied to drain current flows. Notice that the carriers flow like a river due to the potential difference between source and drain. As VD increases, when it reaches a certain value, the river's flow disappears right before the drain. This point corresponds to the pinch-off point. Then, if VD is increased further after pinch-off occurs, the diagram looks like this. Notice that beyond the pinch-off point, you can visually see that carriers are accelerated by the electric field and flow into the drain, as if falling over a waterfall. After all, the reason drain current flows is due to this electric field. This is the answer to the second question.
Thanks, Zundamon. I understand now. But I have one simple question. Why is the depletion layer that forms in N+ thinner than p-silicon?
Good question. This is because there is a large difference in doping concentrations between N+ and p-silicon. Generally, a depletion region tends to spread toward the lower concentration side. The reason is that the charges of the ions within the depletion region must balance each other in order to terminate the line of electric force. Since on the lower concentration side, a wider region is required to provide enough charge. It's the same in MOSFET. In MOSFET, the drain and source are very heavily doped, as indicated by N+. This plus means very heavily. On the other hand, p-silicon in the substrate is not as heavily doped. As a result, the depletion layer spreads widely toward p side and hardly spreads at all toward the N+ side.
Thanks, Zundamon. I understand.
Then, in the next chapter, let's answer the final question. Finally, let us consider the last question. Why does the drain current saturate in the saturation region? The reason is that even if the drain voltage is increased after pinch-off, the voltage applied to the pinch-off point remains constant at VD sat. Therefore, the number of electrons supplied to the drain from the pinch-off point remains constant. This is why drain current is constant, regardless of an increase in the drain voltage.
Hey, Zundamon, thank you for reading the explanation from the textbook exactly as it is written. However, I'm not convinced by that explanation. I have two questions. First, doesn't the drain current depend on the channel length? Intuitively, if the channel shortens and the distance carrier's travel changes, the current should change too. Second, doesn't the drain current depend on the electric field in depletion region? Intuitively, it seems that the current should increase because the carriers are greatly accelerated by the electric field when they pass through the depletion layer.
I see. That's a good question. Let's answer them in order. First, regarding the question, doesn't the drain current depend on the channel length? The answer is yes, it does. Actually, increasing the drain voltage shortens the channel, and as a result, the drain current increases.
Huh? Doesn't that contradict what you just said?
Calm down, I'm still explaining. But in this case, it doesn't.
Why?
Because we're assuming the depletion layer width is sufficiently small compared to the channel length. I'm sorry if it seemed misleading, but this figure emphasizes the parts where the channel is cut off. The actual scale is as shown here. Therefore, it may seem as if the effective channel length has shortened when the drain voltage is increased. But in reality, the change is so small that it has no effect on the drain current.
Oh, so that's what it is. But wait a minute. So, does that mean the drain current depends on the channel length when delta L isn't sufficiently small compared to L?
That's exactly right. This is particularly evident in short-channel MOSFET, which are designed with a short L. When L is short, the spread of delta L cannot be ignored. In such cases, increasing the drain voltage causes the drain current to increase without saturating. Why does this happen? It is because as the effective channel length becomes shorter, the channel resistance decreases. In electric circuits, it's well known that, as the conductor shortens, the number of collisions between electrons and obstacles decreases, and therefore resistance decreases. It is the same principle. For reference, I also explain from a theoretical perspective. The exact drain current value in saturation region is given by this equation. Note that the equation includes the depletion layer with delta L. This means that the shorter the effective channel length becomes, the more the drain current increases. After all, the explanation that the drain current saturates in the saturation region is merely based on the approximation that delta L is sufficiently small compared to L.
I see. I understand.
Next, regarding the question, doesn't the drain current depend on the electric field in depletion region? The answer is no, it doesn't. The reason is simple. The drain current in the saturation region depend on the number of electrons supplied from the pinch-off point. Here, recall that current is a physical quantity defined as the number of electrons passing through a certain cross-section per unit time. From this perspective, no matter how much carriers are accelerated by the electric field, the drain current remains constant as long as the supply of electrons at the pinch-off point is the bottleneck. This is easier to understand by looking at the band diagram in the pinched-off state. Note that the potential drops sharply in the depletion region, where no carriers exist. In such cases, electrons passing through the pinched-off point accelerate into the drain as if falling down a waterfall. This can be compared to rivers and waterfalls or hose with pinched tip. The amount of a waterfall is determined by the river's flow right before the drop, not the height, right? The amount of water that reaches the ground is determined by the flow at the tip, not the height, right? It's the same principle. Even in a MOSFET in the saturation region, the drain current is not determined by the potential between the pinch-off point and the drain, but by the number of electrons supplied from the pinch-off point. Furthermore, this is determined by the number of electrons supplied from the source, which is even further upstream. Now, recall the equivalent circuit. The voltage applied to the channel near the source remains constant, regardless of the drain voltage. In other words, the size of the channel entrance remains constant, and so the number of electrons supplied from it remains constant. As a result, no matter how much you increase the drain voltage to strengthen the electric field in depletion layer and accelerate electrons, it has no effect on the value of drain current. This is because the number of electrons supplied from the source is the bottleneck. And this is why the drain current saturates in the saturation region.
Thanks, Zundamon. I completely understand.
I'm glad to hear that. This concludes the explanation for today. Here's the summary of this video. Today, I explained pinch-off in MOSFET with the goal of understanding why the drain current saturates in the saturation region. I hope this video helps you understand the topic a little better. If you have any questions about this topic, feel free to leave a comment. Thank you for watching.